We have discussed the valence bond theoretical approach for dihydrogen molecule. Then we have gone on to discuss hybridization which gives us access to polyatomic molecules and their shapes. Once again let me remind you that hybridization is invoked to explain the shape, it is not the cause. Methane is tetrahedral not because it uses sp3 hybrid orbitals, but because of VSEPR. You need sp3 hybridization to describe the system, that is all. Okay. Now that being done, it is time for us to move over to molecular orbital theory. We have already given you a very small executive summary of a comparison between valence bond theory and molecular orbital theory. The advantage of molecular orbital theory over valence bond theory is that delocalization can be handled very easily. It is a general theory and excited states are accessible without any hassle. The problem is, and this is something that we will encounter not today, but in the next class, we are going to see that sometimes it becomes a little too general, it overdoes things. The ionic structure of H2 for example is overemphasized in a molecular orbital treatment. But nevertheless MOT is the most popular way of handling electronic structure at this level at least. Later on you might want to go a little further, but I mean this is really the beginning. So we need to discuss and understand molecular orbital theory. Most of the application of quantum chemistry, quantum mechanics in chemistry involves molecular orbital calculations. Okay. You can use different levels, it is a different issue altogether. Okay. But then when we do that, let us not forget our definition of orbitals. An orbital is a one electron system. So when we talk about molecular orbital, what we mean is a one electron wave function for a molecular system, right. There cannot be any other electron. So what is the simplest molecule that has only one electron and that therefore cannot be handled by VBT in the first place? That molecule would be H2 plus. And already a few classes ago, a few lectures ago, we have shown you the Hamiltonian for H2 plus as well as H2. Okay. There are more terms as you go from hydrogen atom to H2 plus to H2, the number of terms keeps increasing as different interactions come in. Now what we are going to do is we are going to use our good old Born-Oppenheimer approximation and say that nuclei are stationary with respect to electrons. So we are going to hold this capital R internuclear separation to be constant for the calculation, and we are going to royally ignore the kinetic energy terms for the two nuclei. So the Hamiltonian we are going to use really is minus h cross square by 2 me del square minus q e square by Ra minus q e square by Rb plus q e square by capital R. I am not using atomic units here, we should be equally comfortable with both. So for a change let me use this. In the next discussion we have Huckel approximation, perhaps we will use atomic units once again. Okay. So this is our Hamiltonian and it is a one electron system. The difference is that unlike hydrogen atom, it is not a central field problem. There are two nuclei, right, two foci. So you cannot use spherical polar coordinates anymore, you can use elliptical polar coordinates and you can actually get an exact solution for Schrodinger equation for H2 plus. But we will not do it. It has been done. I mean there is published literature, it is there in some textbooks, but you will find that they are there in exotic textbooks. You will not find them in the textbooks that we use, Macquarie or Pillar or even Szabo, because there is no need. Because you put in so much of trouble and use elliptical polar coordinates and get some solution, you cannot use them. You do not know what to do when you bring in one more electron and talk about H2, which is the smallest real molecule. So the thing is this, it is better to start using approximation right away since you cannot avoid it one step down the line. So the approximation that we are going to use is something we have learned while talking about variation method. Remember we had said that since in any case Variation method allows us to change parameters and try and minimize energy with respect to these parameters. How does it matter what kind of functions we use? You might remember that elephant on the opening slide of a couple of the lectures that we had some time ago. Those elephants were drawn using some mathematical function. So, any wave function, whatever is the real wave function, even though we do not want to do it exactly, we can use some sum of Gaussian or Lorentzian or exponential polynomial sums and products of these functions, and we can actually simulate these the correct shape, and that is good enough. So, if we take an appropriate set of orthonormal functions, orthonormality, using orthonormal set brings in some advantages, as we have learned in our discussion of many electron atoms. And here the biggest advantage is that we already have a set of relevant orthonormal functions at our disposal, and they are the atomic orbitals. So, what we do is we generate the molecular orbitals by linear combination of atomic orbitals. This is the first approximation. Of course, later on atomic orbitals are not used and molecular orbitals are used by using just what I said, products and sums of different kinds of functions. But for this course we will stick to linear combination of atomic orbitals, because they give us a nice insight of what is going on, and it can give us fairly good estimates of energies. Okay. So, LCAO as it is called is what is going to be used. For H2 plus, the only atomic orbitals that we need to consider are the 1s orbitals, because where is the electron? The electron will be in the lowest energy state, and there is an energy gap between 1s and 2s. So, this is something where implicitly we have used an important principle that is going to come back and get used many times in our discussion, and that principle is that only orbitals of appropriate energies are going to participate in the linear combination. And later we are going to say only orbitals that have the correct symmetries will participate in linear combination. Correct symmetry and comparable energies. Without that, they do not participate in this linear combination. A little bit of difference in energy is okay, but here the difference would be 1s and 2s. So, no, it it makes no sense in bringing in 2s. You might get a little bit of improvement if you do, but at our level in this course we are good with this. So, the LCOMO we use is C1 1s A plus C2 1s B, and I hope this reminds you of the wave function we had in the valence bond approach. There also we had used the two 1s orbitals, okay, but the difference there was that we started with filled orbitals, right. We started with phi 1s A 1 multiplied by phi 1s B 2, then to that we added phi 1s B 1, phi 1s B 2, and then we proceeded. Here we do not bother about the electron to start with. We are more interested in constructing the wave function, and then we will fill in the electron when it is appropriate time, right. But let us work with this molecular orbital to start with. C1 1s A plus C2 1s B. So, you take square of that, this will give you probability density, that is C1 square phi 1s A square plus C2 square phi 1s B square plus 2 C1 C2 phi 1s A phi 1s B. Now, see, is there any reason why in these two terms C1 square should be different from C2 square? We had used exactly similar argument for valence bond theory also. There is no reason why any of these two orbitals will make a different contribution. So, it makes sense to say that C1 square equal to C2 square or C1 equal to plus minus C2. Okay. So, that we can write when C1 square equal to C2 square, when C1 equal to C2 we write C1 equal to C2 equal to Ca, and when C1 is equal to minus C2 then we equate it to Cb. Of course, this is a bad choice, well I should not say of course, actually this is a bad choice because it is better to write B here and A here for reasons you will see very soon. Alright, so what is the wave function then? The wave function, the first wave function where we use a linear combination with plus sign is Ca multiplied by phi 1s A plus phi 1s B. So, in the subsequent discussion most of the time we have not written phi, we have simply written 1s A plus 1s B. What about psi 2? Psi 2 would be Cb into 1sa minus 1sb. And I think most of you would know already that this plus combination is the bonding orbital, this minus combination is the anti-bonding orbital. Why bonding, why anti-bonding, we will come to it in its time. But now this is what we have. Generally we like to draw pictures instead of writing algebraic expressions, and this is a picture that we generally draw. We draw two circles for the two s orbitals, and we would put two plus signs to denote that the combination is plus, and for anti-bonding we put a minus sign in one of them to denote that the combination is minus. And in fact it is better for us, since we know about contour diagrams and all, we can look at the contours and understand better. These are the overlapping contours of A and B orbitals. Here the only difference is that you have to put in the plus and minus sign, and you can draw this psi square like this, right, as dots. Remember, we put a dot wherever there is some probability. So we can generate the diagram of psi star, psi square. It will be like this, no node here. Here there will be a node, right, because in this region there is going to be a destructive interference. So if you look at the profiles, take a cross section of this orbital, you will get two peaks for psi plus, the bonding orbital. Here however, one s orbital points up, the other one s orbital points down. This is plus, this is minus, remember. So you are going to get a node, a zero crossing point exactly between the two nuclei. And if you take this psi square, then psi square looks like a circus tent in case of the bonding orbital, and it looks like two circus tents right beside each other for the anti-bonding orbital. So generally what the argument that is given in many textbooks, even though it is not, it is a little bit of a hand waving argument, that there is a build up of electron density, because psi square is more, psi square dr will also be more here, build up of electron density between the two nuclei A and B, and that is why the electron sort of shields the two nuclei from each other and act as a cement for them. Here actually there is a decrease in electron cloud. If you just drew two 1s orbitals and if there was no bonding at all, then the picture would have been something like this. I will draw a normalized picture. It would have been something like this. So in this region you would have this much of electron density more than what you have for the anti-bonding orbital. So generally even in class 11-12 books this is the explanation that is given. So we will not worry about that explanation for the moment, just go ahead and see how it pans out. To start with, let us normalize this wave function. We know that this is what we usually like to do first. So integral psi 1 squared dr in this case will be equal to, well, will it be dr? It will be dr1 dr2, right. There are, it is a double integral again, that will be equal to 1. So you write this, I am going very fast here because this is more or less what we have done in the valence bond theory approach as well. So you expand this, you get 4 terms, and when you look at the 4 terms, they are familiar. Integral phi 1sa phi 1sa dra is equal to 1, because 1sa is normalized. Same is true for 1sb. And what is this? Integral 1sa 1sb d tau, integral 1sb 1sa d tau. You might remember from our valence bond discussion that these are overlap integrals. Remember overlap integrals? These are simply overlap integrals. So what do you have? You have 1 equal to Ca square multiplied by 2 plus 2s. So Ca turns out to be 1 by root over 2 plus ts, 2 plus 2s. Similarly, you can find the expression for Cb, that is equal to 1 by root over 2 minus 2s. I am going at breakneck speed because it is so simple. Please work this out yourself, then only you will understand fully. Good. Now you might remember that overlap integral is actually a function of internuclear separation. We have done at least one of these, this one we have done. In fact, for that we had given you an expression and we had shown you the plot, and it is not very difficult to see that when these two orbitals are infinitely far away, overlap integral is of course 0. As it comes closer, overlap will go up, 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 and finally it will be something like this. What about this? This is a very curious case. Overlap integral when this r equal to infinity is of course 0. Now even in this case, what is the overlap integral? Is it 0 or is it something else? Yeah, do not forget what overlap integral is. You have to do a point by point multiplication of the two wave functions and add. So this is 0. So this is really an example of non-bonding interaction. Here when you have sigma interaction between an s and a p orbital, then what will the overlap integral be like? 0 here, and then when I bring these close together, say this is your p orbital minus plus, change color, and this is your s orbital plus. Now what happens? Is it 1? Is it 0? What is it? For this part it is going to be plus, for this part it will be minus, and the magnitude is same. So it is going to be 0 at r equal to 0, 0 at r equal to infinity, somewhere in the middle it is going to peak. Where will it peak? It will peak in the situation where this s orbital is here. That is where it is going to peak. So for internuclear separation here to, let us say here. Okay. So in our tutorial we have some problems in which you have to work this out. I think you might have done it already in our assignment. Great. So this is what we have. We have expressions for the bonding and anti-bonding orbitals, that is great. And now our job is to find the expression for energy, expectation value of energy, by using these wave functions for bonding and anti-bonding orbitals. We will call the energy of the bonding orbital E1, bonding MO E1, and we will call the energy of the anti-bonding MO E2. Well, it is perfectly okay to call the MOs orbitals, they are orbitals, but I prefer to call them MOs because we are also using atomic orbitals, and by now we have become used to referring to atomic orbitals as just orbitals. Okay. Now let us see what the expression for energy of bonding MO would be, and once again I am going fast because this is now cakewalk for us, right. What is this integral? First thing to do is plug in the value of psi 1 and take out the product of the normalization constant. This is what we get. E1 is 1 by 2 plus 2s multiplied by, in bra vector we have phi 1sa plus phi 1sb. In the ket vector we have h hat 1sa plus 1sb. Of course you should expand and you are going to get 4 terms, and the 4 terms I hope do not look absolutely unfamiliar to us. Similarly, we can get an expression for E2, and point to note is that if you look at E1 plus plus plus, well of course this is also plus. For E2 the integrals remain the same, only in these two cases plus becomes minus, there is no other difference. Okay. Now let us take a closer look at these energies. Do we know these integrals? Have we encountered integrals like this? Integral phi sa h hat phi sa, well phi 1 sa h hat phi 1 sa, integral psi I h psi I, what is it? Isn't it h I I? Integral phi 1 sb h hat phi 1 sb, again that is h I I. You can call it h j j, but they are the same, does not matter. Integral phi 1 sa h hat phi 1 sb, what is that? That is Sij, and integral phi 1 sb h hat phi 1 sa is Sji, but then Si and Sj are equal because if you remember h hat is a Hermitian, and so we can use turnover rule. So these are familiar integrals for us. We might as well write E1 in terms of Hii, Hij, and for now we will write Sij. And whenever we are bored of writing Ij, we are going to go back to S, does not matter. Okay. So E1 turns out to be Hii plus Hij divided by 1 plus Sij. You might as well write H11 plus H12, does not matter. Okay? Perhaps it is better to write H11 plus H12. What about E2? In E2, if you remember, the only difference was that the last two terms had minus, negative coefficients, negative signs. So, plug that in, you get E2 to be Hii minus Hij divided by 1 minus Sij, both become minus. Okay? So, now to go further, we need to evaluate Hii, we need to evaluate Sij. We already know what Sij is. In fact, we already know what Hii, Hij are as well, we are just revising. So, this is your Hamiltonian, this time not in atomic units, minus h cross square by 2 me del square minus q r square by Ri. You can recognize that these two terms constitute a one electron wave function minus q e square by Rj plus q e square by R. This is your this is for the potential energy for attraction between electron and nucleus. Sorry, what did I say? Q e square by capital R is for internuclear repulsion, nucleus repulsion. So, we will club these two together and we are going to write Hamiltonian of one electron. So, now our Hamiltonian has 3 terms. So, Hii is integral phi si left multiplying Hamiltonian operating on phi 1 si. Okay. So, we will write like this. Okay. Same expression, so no harm done. Hii equal to sum of these 3 terms. Now, look at this, 1 by R is a constant at a fixed internuclear distance, right. We are working under the ambit of Born-Oppenheimer approximation. Here I might digress a little bit and I might say that the Born-Oppenheimer approximation does not hold in all cases, but that comes under the beyond approximation theory limit. That is a little more complicated phenomenon. For our purpose, Born-Oppenheimer approximation is actually a very good approximation. We can work without its ambit without losing generality. Okay. So, this is a constant at fixed internuclear distance, fine. So, we can bring it out. What did I do? Sorry. So, I can write like this, integral phi 1 si h 1 electron phi 1 si, we will come back to this, plus q square integral phi 1 si phi 1 si minus q square integral phi 1 si 1 by rj phi 1 sj. Again, I hope that these terms do not look unfamiliar to you, because first of all phi 1 si integral of that, what is that? That is simply 1, it is normalized. Integral of phi 1 si into 1 by rj phi 1 si, what is that? I hope you remember that it is the Coulomb integral j, right. Remember Coulomb integral? Coulomb integral denotes the electrostatic interaction, right. We had worked this out when we talked about dihydrogen molecule in your valence bond theory. And I hope it is not very difficult to see that integral phi 1 si h hat 1 electron phi 1 si, what will that be? H hat, that will be the expectation value of energy of 1s orbital. It does not matter whether I use A or B, this energy of 1s orbital is still the same. So, energy of 1s orbital plus q square by r minus q square into j. Okay. Now, let us evaluate the integral Hij. So, it is not enough to evaluate Hii, right, I want energy finally. So, Hij similarly we can proceed and we can again use this 1 by r to be constant. Hij will be first of all this is the value of energy for your 1s orbital, then q square by capital R, as we know that this but what is this integral of 1 si 1 sj, what is that going to be? That is going to be s, right, overlap integral, it will not be 1, and this integral minus q square integral phi si 1 by rj phi sj, what is that? We know that also, right. So, the first term is E1s into s. Let me work that out, because I think I made a careless statement just a few minutes ago. I am working this out. What is it? H hat 1 electron operating on phi 1 sj gives me E1s. So, if I write it in bracket notation, we have in bra vector phi 1si. So, what will I get? This becomes E1s multiplied by phi 1sj of course. So, you take this and plug it in, and moreover you take this E1s out, you are left with E1s multiplied by integral phi 1s I phi 1s j, that is your S. E1s S, next one will be just q e square by r multiplied by S, same S is there. Then if you look at the third integral, it is k, is not it, exchange integral, or I did not tell you this name earlier, it is also called resonance integral, because here you are considering 1s I and 1s j in the same integral, right. So, exchange. So, please remember, okay, we will come back to that later, but let us write like this, minus q e square into k, and remember that k is a purely quantum mechanical concept, there is absolutely no classical counterpart for k. Fine. So, we know HII, we know Hij, we of course know Sij, it is equal to S. So, I have written Sij equal to S here. Now, let me plug in the values of HII, this is HII, I hope you recognize E1s plus, I have taken q e square common, q e square multiplied by 1 by capital R minus j, and Hij is E1s plus q e square multiplied by S by R minus k. So, E1 will then be equal to, if I now collect the coefficients of E1s, q e square by R and minus q e square. So, what will be the coefficient of E1s? Well, E1s into 1 plus S, is not it, 1 from here, S from here. What will be the coefficient of q e square by capital R? Q e square by capital R, so 1 from here and S from here, so 1 by S. Minus q e square, what will be the coefficient? You take minus outside, from this term you get j, from this term you get k. Minus q e square multiplied by j plus k, that is E1. So, E1 then turns out to be, you just simplify, divide throughout by 1 plus S, you get E1s plus q e square by capital R minus q e square multiplied by j plus k by 1 plus capital S, right. Similarly, you can work out an expression for E2, and that turns out to be E1s plus q e square by capital R minus q e square into j minus k divided by 1 minus S. So, see, E1s plus q e square, what is that? That is simply energy of 1s orbital plus the nucleus repulsion term. Q e square by R is the potential energy for nucleus repulsion. So, this is the energy that we get if there is nothing else happening. Okay. So, this is basically destabilization, this q e square by R is capital R. So, when you bring in the third term, q square into j plus k divided by 1 plus S or minus q square into j minus k divided by 1 minus S, this third term decides whether you get net stabilization or net destabilization. So, that depends on the integrals. And remember, we are constructing these integrals using 1s orbital to start with, but that will obviously not give me very good result. So, what is done is, as we have discussed, hydrogen like orbitals, STOs, GTOs, in 1s orbital expression, that Z is kept as a variational parameter, because here also you have 2 nuclei, right. We do not have a second electron yet, but that Z instead of Z you write zeta, a variational parameter. So, that is varied, and you can also vary n, and using variation method you can find the upper bound for the energies. That is how you find the expressions for E1 and E2 for given values of capital R. Okay. Another thing to remember is that J, K, S, these are also integrals that depend on the value of capital R. Okay. So, there is a very strong dependence of the energies, and this is what you get. For E plus you get a minimum and then it goes up, for E minus it goes up all the way. So, this is how the energy of bonding orbital varies as a function of R. This is how the energy of bonding orbital varies as bonding, anti-bonding orbital varies as a function of internuclear separation. At equilibrium bond length you can see that stabilization, the amount of stabilization that you have of the bonding orbital is actually less than the amount of destabilization that you have in the anti-bonding orbital. So, if you have 1 electron in bonding orbital, 1 electron in anti-bonding orbital, cis energy of the system will not be 0, it will be more than 0, right, and that is often explained by these hand waving arguments using this kind of orbital picture. Okay. So, we have already studied sigma bonding with 1s orbitals. I leave it to you to work out the at least shapes of bonding and anti-bonding orbitals using 2p orbitals. This is from one of the textbooks, I have forgotten which one, but this one is wrong, please do not look at that. And this is what you get for pi bonding using 2p orbitals, okay, just side on overlap. And one thing that you should remember or know or understand is that symmetry of orbitals is often used as very important parameters. For the hydrogen molecule ion, for bonding orbitals it is symmetric with respect to inversion. So, it is called sigma g, g for Gerarday. The anti-bonding orbital is antisymmetric with respect to inversion, that is called sigma u. Do not think that always bonding orbitals are Gerarday and anti-bonding orbitals are un-Gerarday, that is not the case. If you look at the bonding pi orbital used by side on overlap of 2p orbitals, you see that this bonding orbital for pi is un-Gerarday and anti-bonding orbital is actually Gerarday. Okay. So, we are going to use this in the nomenclature of MOs when we talk about actual molecules, and using this I think you already know what are the types of bonds: sigma, pi, delta. Okay. These are examples of what kind of bonds are formed using different orbitals. Again I leave this to you as an assignment. In case of any difficulty, any question, please feel free to contact us or ask in the open session. This completes our discussion of H2 plus, little longish module, sorry, very fast, but it is a repetition of what we have done earlier. I am sure you will be able to handle it. With this knowledge we next discuss H2 molecule. We bring in another electron and use the same orbital, perhaps with modification for things like shielding, and we see how that compares with the earlier valence bond approach. And after that we go on to homonuclear diatomics of second row, then heteronuclear diatomics, polyatomic molecules. Finally, we will talk about pi molecular systems.